In this video, we are going to handle these four series and they are about absolute convergence. Let's take a look at the first one. So number one, we have the sum n goes from 1 to infinity, and then we have -1 n plus 1 divided by n squared. Alright, so this one is clearly an alternating series, so then we have to go by the alternating series test. So before we do that, so I'm going to write this. So Bn is equals to 1 divided by n squared. Now, you are going to ask me a question. Hey, Bn is 1 divided by n squared. Isn't that Bn is the entire series? So let me remind you, this is very important. This entire series is called An. Because when we talk about series, we talk about the sum of An, right? So the reason we use Bn is we want to take away the factor of the alternating series. Like we want to take away the plus, we want to take away the minuses. Because due to the -1 raised to the n plus 1, so when you write out the sum of all those numbers, you will get a plus, minus, plus, minus, plus, minus, right? In order to take that away, we call it a Bn. So the Bn is just 1 divided by n squared. And then we also need a Bn plus 1 that is equals to 1 divided by n plus 1 squared, right? So first, when you perform the alternating series test, first thing that you have to show is you have to show that Bn plus 1 is less than or equal to Bn. This is easy. So when n is equals to 1, we have 1 divided by 1 plus 1 square, right? Which is 2 square. And this is 1 square. So 1 divided by 4 is less than 1. And then let's do one more. Usually test n equals to 1 is enough, but I would like to test one more. So this one, when n is equals to 2, 2 plus 1 is 3, 3 squared is 9, less than or equal to, you square the 2, then that will be 1 divided by 4. And then number 2 is you have to show that the limit as n approaches to infinity of Bn is equals to 0. This is even easier. 1 divided by n squared, so that is 1 divided by infinity, that is equals to 0. So the series is convergence by the alternating series test, right? So alternating series test, you can call this AST, alternating series test. But that is not the end. We also need to show that the absolute value of An, so the absolute value of An, what is that equal to? That means we have to take the absolute value of the given series, so that is -1 raised to the n plus 1 divided by n squared. So when you take the absolute value of that, you just take away the top, right? So the alternating term is gone instantly. And then we only have the absolute value of 1 divided by n squared. Do we still need the absolute value? The answer is no, because 1 divided by n squared is always positive, right? So that is just 1 divided by n squared. And then this is the absolute value of An. So is this convergent or divergent? So this is what? Usually, when you look for a problem from a book, usually this one you have to use the P series. So this is a P series. And then P is equals to 2. 2 is greater than 1. So that means the absolute value of An is convergence. Now, you need to pick up your highlighter. So we have two conclusions, convergence and convergence. So that means overall, the sum of An is convergence absolutely. Or you can say it's absolutely convergent. So that is the first problem. Usually, you have to use a P series, but since I gave you multiple examples, the next one is something that you do not need to use the P series. So that's why you need to deal with multiple examples. So usually, it's a P series. What if the problem doesn't want you to deal with P series? So that's why we have problem number 2. So problem number 2, we have the sum, n goes from 0 to infinity, -1 raised to the n, so that is still an alternating series, e raised to the n squared. Alright, so this is an alternating series, so the Bn is 1 divided by en squared, so we just take away the alternating term, and then we also need to find the next term, which is 1 divided by e to the n plus 1 squared. All right, so number one, we have to show that Bn plus 1 is less than or equal to Bn. When n is equals to 1, what do we have? We have 1 divided by e to the 2 square, right? 2 square is equals to 4. And then this is a 1 square, which is still 1. So the bigger denominator is always smaller. And then you can test one more, but you don't need to. When n is equals to 2, 3 square is 9. And then this is 2 square is 4. All right, so number one is true. And then number two, you have to show that the limit as n approaches to infinity of Bn that is equals to 0. So that will be the limit as n approaches to infinity, 1 divided by e to the n square. So that will be 1 divided by e to the infinity. That is 1 divided by infinity. That is equals to 0. So number one is true. Number two is true. Therefore, using the alternating series test, so the alternating series test, the series is convergent. AST, alternating series test. We just proved that the series is convergent. Now we have to take one step deeper. That is, we have to take the absolute value of n. So we also need to take care of the absolute value of n, which is the sum of absolute value of negative 1 raised to the n divided by e to the n square. Then this absolute value take away the alternating term, then the top is just a 1 and then the bottom is e to the n square. You still take the sum of that. So when you do so, do we agree that do we still need the absolute value? The answer is no. Take a look at the denominator. N square is always positive, right? And then e is around 2.7. 2.7 raised to some power is always positive, so we only have this, right? Oh, by the way, this one I forgot to do the square. Not the square, the summation. Okay, so this series, is this convergence or divergence? So this is a what? This is a geometric series. So other than P series, sometimes you have to deal with geometric series. So how do you make this geometric? So you raise the whole thing to the n square, and then the inside, the base, we have 1 divided by e. So the top 1 raised to any power is still 1, right? So this is a geometric series, and then the common ratio r is equals to 1 over e, and then the absolute value of common ratio, 1 divided by 2.7, is less than 1. So therefore, this geometric series, the one we have right here, is convergence by, is a geometric series, okay? And is convergence, right? Convergence. Okay, so what conclusion do we have? We have a convergence using geometric series and then a convergence using alternating series. So therefore, the given series, whatever that is, negative 1 to the n raised divided by e to the n square, is absolutely convergence. All right, so that will be number 2. So other than P series, sometimes you have to use geometric series. And then we moving on to number 3. We have trig functions. So number 3, we have the sum n equals to 1 to infinity. We have cosine n pi divided by 3 divided by n square. All right, so here we have a cosine. So how do we deal with cosine? Oh, by the way, is this an alternating series? So when n is equals to 1, cosine of pi over 3, that is in the first quadrant, right? So in the first quadrant, x is positive. And then when n is equals to 2, cosine of 2 pi over 3, that is in quadrant 2, x is negative. And then when n is equals to 3, we have cosine 3 pi over 3, which is cosine of pi, right? So cosine of pi is x is in the between the second quadrant and the third quadrant, so which is on the x-axis, so x is negative. And then cosine 4 pi over 3, so that means x is in the third quadrant, then it's negative. So we have positive, we have negative, but we have negative and then negative. So that means, that tells me this is not an alternating series. then we cannot do the alternating series test, the Bn and the Bn plus 1. That is not going to work. But for cosine, we can say that the cosine is between -1 and 1, right? So cosine of n pi, or you can say pi over 3 times n, this is between -1 and 1. Cosine is jumping between -1 and 1, right? If you check out the graph of cosine. But you might ask me, hey, that is not cosine of x, that is cosine pi over 3. The pi over 3 affects the period only. The pi over 3 doesn't affect the amplitude, which means the pi over 3 doesn't affect the range. So this is still between -1 and 1. And then once we take the absolute value of that, we take the absolute value of each side, what do we get? The absolute value of -1 is no longer 1. So if when you take the absolute value of that, okay, let me just give you the graph. So cosine, right? It is supposed to be like this. That is cosine. So it's jumping between y equals to 1 and y equals to -1. When you take the absolute value of that, the piece below the x-axis is gone instantly. It's not disappear. So when you take the absolute value of that, it becomes this. So we have to erase this piece. So now cosine absolute value is between 0 and 1. So back to this problem, then this is where 0 less than or equal to absolute value of cosine pi over 3n, and then the absolute value of 1 is still a 1, right? So since the series has divided by n squared, then we divide each term by n squared. So 0 divided by n squared is still 0, and then this is cosine pi over 3n divided by n squared, and then we have 1 divided by n squared. Okay, and then we take a look at the 1 divided by n squared. What is the sum of this? The sum 1 divided by n squared. What kind of series is this? This is a p series, and the power is equals to 2. Since the power is greater than 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, doesn't matter what power you use, that is greater than 1, then what do we say? We say that the series is convergence, right? So if you plug this into an inequality, you have a 0 less than or equal to something less than or equal to a convergence. So 0 is already convergence, then the stuff between the 0 and the convergence has to be convergence. And then this is the summation of absolute value of an. So we just prove that the absolute value of the given series is convergence. So using the definition of absolute convergence, we say that the given series cosine n pi over 3 divided by n squared is absolutely convergence, right? So absolutely convergence. So that is the end of this problem. All right, doing good so far. And then moving on to the last one. So the last one, number 4, is a very interesting problem. It's not absolute convergence, but I would like to put that in these videos. N goes from 1 to infinity. We have -1 raised to n plus 1, and then times arctangent. I want you to take a look at the graph of arctangent. So the graph of arctangent, still remember that? The graph of arctangent is between pi over 2 and -pi over 2. So this is the graph of absolute convergence. All right, so let's take the absolute value of this. So the absolute value of this, the absolute value of an, that is the absolute value of -1, n plus 1, and then arctangent n. So that take away the absolute value. So we only have arctangent of n. Now, when n goes from 1 to infinity, it goes from 1 to infinity. So that means when the x value, so this one treat that as an arctangent of x, when x is 1 or higher, what do we say? The y value is always positive, so that means we don't even need to consider the absolute value, because when n is greater than 1, arctangent of 1 or above is always positive, then we don't need to consider the absolute value. So that is arctangent of n. Okay, so this one, what happened when n approaches to infinity? So the limit as n approaches to infinity of arctangent of n What is that equal to? The arctangent of n as n approaches to infinity. Let's use the highlighter a little bit. So that means we are talking about this piece, right? So when n goes all the way to infinity, what happened? So as n approaches to infinity, this is equals to pi over 2, right? As n approaches to infinity, because pi over 2 is a horizontal asymptote. As x or n gets really, really big, the y value is getting closer and closer to pi over 2, but will never equal to pi over 2. So pi over 2 is not equals to 0. And then what do we say? What does that mean? Pi over 2 is not equals to 0. So you have a series, right? A series of an. And then if you look all the way to the last term, you see that you are still adding pi over 2 or some numbers close to pi over 2. That means you are still adding some values to the sum. As a result, the sum is going to be really, really big. Then what is your conclusion then? The conclusion is, since the limit is not equals to 0, then the series is diverged by the nth term test. What is the nth term test? The nth term test is right here. So you have the sum of an, so that is equals to a1 plus a2 plus a3 plus a4, and then you keep on going, right? So as n approaches to infinity, you are looking at the last couple terms. So the last couple term, they are value that is close to pi over 2 and not equal to 0. That means as you add up this value, you are adding up many, many numbers, right? As you approach to the end, you are still adding some serious value to the sum. So that means you are still adding some number that are not close to 0 to the sum. That makes the sum really big. So the sum is big. That means the sum is equals to infinity. As a result, since the sum is so big, then we say the series is divergent. That's the conclusion. The given series is divergent by the nth term test. There is no absolute convergence in this problem. Now, I know, what if the limit is equals to 0? If the limit is equals to 0, that means the last couple terms, they are so close to 0, so adding those values to the sum won't make the sum becomes really, really big. So the sum is really determined by the sum of the first couple terms. So in that case, the entire series is convergent. Alright, so that is the end of this video. If you think my instruction is helpful, let me know in the comment section below and like the video as always. Subscribe to my channel, share the video for me. I'm sure many people are looking for similar types of videos. I will see you all in the next lesson. Signing off for now.